Hello friends, so today we are going to do the questions from the last, that is from the 24th, and for the physics session, and these are the memory based questions. And a second. So we are going to solve around 23 or 24 questions, and so, 1 second. Okay, I think I lost the file. Let me get the file and come back. I think this will be, yeah, I think this is okay. So today we are going to solve questions from JEE Mains, and these questions are from 24th 2026, and all the questions we are going to solve from the physics, and for both morning as well as our evening session. And please remember, these questions are memory based. So first question, it states that a uniform rope is supported by two level pins supports as shown in the figure. The mass of the rope is m. Find the tension at the midpoint. So basic figure is given to us. So we are given that we are having two pins, and between these two pins a rope is connected. So this is the rope, and it is making an angle of 30 with the, and we are supposed to find out what will be the tension at the midpoint. Therefore we can consider, suppose this is a midpoint, so we are going to consider 1/2 of the rope, and for this 1/2 the rope, let us suppose this point is A, this point is B, and this point is C. So AB and BC are symmetrical with each other, so we can consider only 1/2, that is our, this is point A and this is our point B, and we are given this angle is about 30 degree. So point B is our the lowest point, so specifically at point B there will be tension T, and that will be entirely our horizontal. Let us call this as our TS. And at point A we can, this is point A, and we can just divide this tension T, this angle 30, so this will be also 30, and we can divide, let us suppose this tension is given as our Ts, and we can divide this tension into two components. This will be a Ts sine of theta, and we are going to have this as our Ts cos of theta. So this is the basic, and somewhere here there will be a mg in the downward direction. Mass we can calculate later on what is the mass. And if we assume that this complete rope AC is having a mass of m, then 1/2, that AB, will be having a mass of m by 2. So this will be somewhere here m by 2. And please remember that it is nothing but our symmetrical part. And so there are two components at point A, and everything is equilibrium. Therefore we can write that for half rope AB, and the midpoint is our B, so you can see at midpoint B the tension is horizontal. The tension is horizontal, and okay, sorry, this is, let us suppose, T naught, a little different. So this is T naught. So tension is horizontal, and let us call this as a T naught. Therefore we can say this T naught will be equal to our Ts cos of 30, which gives us our Ts multiplied by square root of 3 and divided by 2. Similarly, we can apply the equilibrium for our vertical. You can say for vertical, in upward we are having our Ts sine of 30, and in the downward we are having mg by 2. Sine 30 is our 1 by 2, so this comes as Ts multiplied by 1 by 2 is equal to over mg by 2. So this 2 and 2 is going to cancel out, and this gives us that our Ts is equal to our mg. And so we can simply substitute it and get our tension at the midpoint. So we can substitute our Ts here, so we get that our T naught will be equal to our square root of 3 2 multiplied by mg. So this is the tension at the midpoint which was our asked for. Next question. So it states that find the force on the charge Q of 1 coulomb due to a uniformly charged rod as shown in the figure. This question is not complete basically, it has lots of discrepancy in it, but we can get the basic idea because lots of information is required and that is missing in this particular question. So this is the rod given to us and it is having a charge of capital Q, and this is our charge Q, and it is at a distance of 2 centimeter, on the one end of the rod, and the length of the rod is given to us as our 10 centimeter. So we are going to consider that let us assume that our L is the length of the rod and Q is our total charge. Therefore, we can say the linear charge density of the rod, linear charge density of the rod, let us call this lambda, and this lambda will be equal to over Q upon L. And somewhere here we are going to consider a small element, that is our dx, and this small element dx is suppose having a charge of dq. Therefore we can say that charge element dq will be equal to lambda times dx, and this charge element is suppose this distance is our x. So we can find out the force due to this charge element dx. You can say the force due to the element, and so for that let us find out our electric field. So we can say that electric field due to dq, and suppose that is our dE, which will be equal to our k small charge and distance square. Therefore we can write that the force on charge q, that is our dF, is equal to q times dE, and we get that our dF will be equal to, this comes as k and q lambda dx and our x square. Now we can easily find out our total force. Total force, that is our F, will be equal to kq lambda, and let us assume that the ends are respectively at A and at B. So this comes as dx and our x square, and so we get the force F will be equal to kq lambda 1 upon A minus 1 upon B, and we can easily find out our 1 upon A, 1 upon B, and that will be 0.02 minus, and this comes as 0.12, which will be approximately equal to 41.67. Therefore we get that the force, and this will be k is our 9 into 10 to the power 9, charge is our 1 microcoulomb, so minus 6, and multiply by lambda and multiply by 41.67. Therefore we get that our value of force will be equal to 3.75 into 10 to the power 5 times lambda. And like I said, there are some critical information missing in the question, so that is require some kind of lambda, and other information is also required, but we get the basic how this question can be solved. Next question, it states that a particle moves in a vertical circle. Find the speed at a lowest point Vs so that the tension in the string becomes 0 at point A, which is 60 degree from the vertical, measured from the center. Basic figure is actually given to us. So we have a circle, and this is our vertical, this is horizontal part, center, R is given as a radius, and the point A is somewhere here. So this is point A, and its angle with the vertical is given as 60 degree. So we want the tension at this point A should be equal to 0. Okay, that's what we want. And so here for this point A, let me redraw it. So this is our center O, so this is our OA, and we have vertical, this is our 60, and here our mg will be in the downward direction, which we can divide into two components. So this will be our 60, so we are going to get this as mg cos of 60 and mg sine of 60, and tension will be also in this direction. Therefore we can say that our radial force balance, radial force balance, and that equation will be equal to T plus mg cos of theta, and let us suppose the velocity at point A is our VA. So which we get, this is m VA square and divided by R. And here it is capital R, so let us put this capital R. And we require radial force balance at point A. At point A. And we want that at point A this tension should be equal to 0. Therefore we get this as our mg cos of our 60 will be equal to m VA square upon R. M and m cancels out, and cos 60 is giving us 1 by 2. Therefore from here we can write that velocity at point A will be equal to g times r and divided by 2. So this is the velocity at point A, and let's find out what will be the height of this point A. So we know this is given to us as r, and we can easily find out this height. This will be nothing but our r cos of theta, here r cos of 60. So this will be r cos of 60. So this total height will be equal to r plus r cos of 60, and let us call this as h. So we can say that our height of point A above the lowest point, above the lowest point, that is our h, and it will be equal to r plus r cos of 60, and cos 60 1 by 2. Therefore we get that value of h will be equal to 3r by 2. Now we are going to use energy conservation from the lowest point to the point A, and lowest lowest point is, let us suppose this point is our B. So lowest point is our B. So energy conservation, when it is going to move from B to A, and at B, let us suppose it is having a velocity of V0. Here it is having a velocity of V0. Potential energy at B will be equal to 0. So we can write this equation that our half m V0 square will be equal to over half m VA square plus mgh, and h we have found as our 3r by 2, and this mass cancels out throughout, and we already know our VA, or rather VA square, therefore we can write this as our V0 square is equal to, this comes as our, okay, we can cancel out 2 also, so this comes as a GR upon 2 plus 3GR. So we get V0 square is equal to 7 by 2 times GR, and if you remove the square root, it will be our square root. So this is the velocity at the lowest point, so that the tension at A becomes is equal to 0. Next question. It states that the velocity of the particle varies with the position as shown in the graph. Find the correct variation of acceleration with its position. So basic graph between the velocity and the particle is given to us. This is our position and this is velocity v. The graph is falling like this. This is the graph, and based on this we have to find out what will be the graph of our acceleration and the position. And so from the graph we can say that the velocity is decreasing linearly, okay? And at x is equal to 0, let us suppose the velocity is given as v0, that is a maximum velocity. So we can write the equation, and can say that the equation will be equal to our v is equal to our v0 minus k times x. V0 is our maximum velocity at x equals 0, and k is the positive constant, which is a representation of the slope. And we can also write that our acceleration, which is our a, is nothing but our dv by dt, and we can just modify it with respect to the displacement. So we can say this will be over dv by dx, and this comes as dx by dt, and dx by dt is nothing but about v, and this comes as our dv by dx. Okay. And this dv by dx we can easily find out from the graph. Okay. So we can say that this dv by dx is nothing but the slope of vx graph. So we can say this dv by dx is our slope of velocity position graph, and this slope is our negative, and it is constant. Therefore we can write that our dv by dx is suppose equal to some m minus of m, where m is a positive constant. M is our positive constant. Now we can express this in terms of our acceleration. So we can say that our acceleration will be equal to, this is our dv by dx, that is equal to minus of m times the velocity, which gives us minus of m times v. And we can also write our acceleration as acceleration is equal to, we have our v dv by dx. Okay, we already know the equation for v, and therefore we get this as our v naught minus kx and times minus of k. So this gives us that our acceleration will be equal to minus v naught plus k square times x. So this is the basic equation of our acceleration, and k is basically our constant, and this is the representation of our acceleration is varying, or we can say varies linearly with x. This conclusion we can easily draw from this particular equation. And we can also say from here that the slope will be positive, okay, and the intercept will be negative. Therefore we can draw our acceleration graph. So this is our x and this is our acceleration, and when x is equal to 0, from here we can say that our x is equal to 0, we are going to have an acceleration that is our negative. So it is going to start from somewhere here, and then it is going to move towards the x-axis. So this is the graph of our acceleration relation. Next question. It states that for a person standing at midpoint O, the direction of current in loop A is clockwise and in loop B is anti-clockwise. The magnitude of current in each loop is shown as in diagram. Loop A is I and 4I in loop B. Then the direction of magnetic field at point O is. So this is a little bit tricky, but it is very easy to solve. Okay? We only need to understand how the direction of the magnetic field is going to, what will be the basically direction of the magnetic field. And the person is somewhere standing here. This is O, and this is our coil A, and this is coil B, and the direction of this is our I, and here it is given as our 4I. And so this interpretation of our you can say, now the person that is standing at O, if it is looking towards coil A, with respect to, if it is looking toward coil A, and from there it can easily see that the direction of the current in coil A will be clockwise. And when this person standing at O will be looking toward coil B, here also the direction will be clockwise. So the direction of the magnetic field in both is our clockwise. So magnetic field is clockwise here also, and magnetic field is clockwise here also. And so it means both loops are having clockwise direction of the magnetic field. And but if we want that our and we are supposed to find out the direction of magnetic field at point O. So for point O, let us call this as our B1 and this is B2. So for point O, our B1, B2 will be on this side, and our B2 will be, B1 will be in this side, and O is at the midpoint. Everything is same, only the magnitude of current is different. Therefore we can say with respect to magnitude that our B2 will be greater than B1. Therefore the net magnetic field at point O will be towards our coil B. So this was a little bit tricky here, only because the direction of current in the coil individually we look is opposite, but when the person or anybody who's standing at point O looks towards it, he finds that the magnetic field direction in coil A as well as coil B is both clockwise. Next question. It states that find the current through the ammeter in the given circuit. So circuit is given to us, and this is our ammeter, which we are supposed to find out the current. And we are having a capacitor which is connected between diagonally here. So we are given this as a 6 ohm, 8 ohm, 4, 8 as well as 8, and this is our 10 volt, and this is our ammeter. So basically we are interested in finding out the current through our 8 ohm resistance. So we are going to find out current through here. So this is a capacitor C, and we know because under steady state condition this capacitor will be acting as an open circuit. Okay, so we can just ignore this part because nothing will be flowing through here because it is a open circuit. You can say that at steady state our capacitor is acting as a open circuit. Therefore we can redraw our circuit, and the circuit will be now quite simple. So this is our 6, 4, 10, and we have our 8. This is our 8, and this is also our 8. And from here we can easily see that these two are in parallel, and if these two are parallel, they are having same value, so their equivalent resistance will be equal to their half, that is our 4 ohm. So you can just draw the equivalent circuit. So ammeter, we have, for the time being, we are just going to ignore it. It is there, but we are just going to ignore it. It doesn't matter. This is 8 and this is 4 and this is 4. Now these two are in series. In series, their equivalent will be equal to our 8 ohm. So this comes as our 8, and this will also our 8. So this is 8, 6 and 8. And once again, these two are in parallel. So these two are in parallel, so we are going to get their equivalent resistance will be equal to 4, and this is 10. So we can just draw it. So this will be 6, and this will be 4, and this is 10 volt. and these two are in series. Therefore, you can say we get this as our this is our 10 and this is our 10. Now we can find out current through here. Let us suppose this current is our I. Ohm's law. So you can say that current I will be equal to the applied voltage and the equivalent resistance, which gives us 1 ampere. So the current total we can say that our total current is equal to our 1 ampere, and this we have to find out the current. So this 1 ampere current, we can say this will be flowing from here, and so at this position, let us call this a position A, this current will be dividing. So partially it will be coming here and partially it will be going here, and we can just write for this equivalent resistance. Okay, so this is our 8 will be 4, and this is our plus 4 will be equal to 8. So let me draw it once again. So this is our 8 ampere, and now we can just draw our ammeter, and this is our the equivalent resistance, that is our 8. So this is 8 and this is our 6, this is our 10, and we found out that from here we are going to get current as our 1 ampere, and this both are same resistances. Therefore we can say the current will be equally divided between the two. So let us assume that from here current flowing is IA. So we can say that current IA will be equal to 1 by 2 ampere, and that is equal to 0.5 ampere. So in this case we have to take care of one important part, that when we find out this current I, this current I is the current that is being supplied by the voltage source. Okay? Therefore we are going to put this current with respect to the voltage source, and then we are supposed to find out current flowing through here. Then we are going to use simple our KCL, but we have to remember that after A, the current whichever it is flowing in this direction, it will be dependent upon the value of the resistances which are connected here. And like I said, this is current IA. This current IA will be only dependent upon our 8 ohm resistance, and if I assume this current is our IB, this IB current will be dependent upon this entire resistor network. Therefore here I connected my IB and equivalent resistance, that is our 8 ohm. So this is a little bit tricky part here, but is quite easy to understand. So our IA is our 0.5 ampere. Next question. Okay, it states that a regular hexagon has resistance R on each side. Find the equivalent resistance between points A and B, which are two adjacent, sorry, it is not adjacent but opposite. And this question is little bit tricky in the sense because here we can use the folding concept, okay, but it is not easy to understand the concept of folding, because with respect to how to apply it, where to apply it, and when to apply it. Okay, so if you are not able to understand the folding concept, we can use our normal process of our KCL to find out which of the vertices will be at equipotential. That's the basic purpose of our folding, or you can say symmetricity. Okay, let me draw the figure first. and then we are going to use our KCL to find out which of the vertices will be at same potential. So this is our A and this is our B, and let us assume this is our A, this is C, D, and this is our E, F, and this is our O. And for our symmetricity or folding concept, we can join, or we can say we can combine equipotential points. Equipotential points. But the only problem is that it's not easy to identify these equipotential points. So we are going to use the traditional way using KCL and try to find out which of the points will be equipotential. And for that, we are going to assume that we have connected a hypothetical voltage source between A and B. And so voltage source at A, let us suppose is a VA, and at B it will be equal to 0. And similarly, at C is our VC, at D is our VD, and this is our VF, VE, and V0. So these are the various voltage sources which we have assumed. And now let us assume, start with KCL. Please remember, we are not going to use the basic, that is our symmetricity concept or folding concept here. Okay, we are going to use the more traditional way to find out the points which are at equipotential, okay, because it is not so much easy to identify when and how to use the principle of symmetricity or principle of folding. Okay. So we are going to use our basic, so we are going to use the KCL at node AC. And I'm going to write it the KCL with respect to our voltages. Okay. So this will be our incoming, and there will be two outgoing, and their algebraic sum will be equal to 0. And we know, and therefore we can write this as our VC minus VA upon R plus VC minus VD upon R plus VC minus V0 upon R will be equal to 0. And if you multiply by R, okay, so this R will be gone away, and we can write this about 3VC and minus VA minus VD minus V0 is equal to 0. Let us call the equation number 1. This process will be lengthy, but you are going to get the correct answer. Okay, there will be no confusion. Similarly, KCL at node F, and node F is our A, O, and E. Therefore, we can write the equation will be equal to our VF minus VA upon R plus VF minus VE upon R plus VF minus V0 upon R is equal to 0. Once again, we can just take away this R, and we get this as our 3 times VF minus VA minus VE minus 1 second 1 2 3, yeah, 3 times VF VE V and V0 is equal to 0. This is our equation number 2. Now we come to a node at D. node D, and we can write this as our Vd minus Vs upon R plus Vd minus Vb upon R plus Vd minus V0 upon R is equal to 0. And we know that our Vb is equal to 0, so we can just ignore it, and this R goes away. So this gives us that our 3 times Vd minus Vc minus V0 is equal to 0. Equation number 3. And then we come to a node at E. Okay, so node E, we can simply directly right now, okay, we can say this will be equal to 3 times Ve minus Vf minus V0 is equal to 0. And then we are having A, B, C, D, E, and we have our knot at the center. We can say this is our node O, and node O will be giving us V0 minus Vc upon R plus V0 minus Vd upon R plus V0 minus Ve upon R plus V0 minus Vc upon R is equal to 0. And this gives us 4 times V0 minus Vc plus Vd plus Ve plus Vf is equal to 0. So this was our equation number 4, and this is our equation number 5. So we were able to find out 5 equations. The only task left is solving it. Okay. So we are going to start with our 1 minus 2. Okay. So 1 minus 2 is going to give us this is about 3Vc minus Va minus Vd minus V0, and minus we are having 3F minus Va minus Ve minus V0 is equal to 0, which gives us 3 Vc and Vf we can combine. So this becomes Vc minus Vf minus, and V0 and V0 are going to cancel out. Similarly, Va and Va will also cancel out. So we get this as minus Vd minus Ve is equal to 0. Let us solve this equation number 6. Similarly, second part we subtract 3 and 4. So we get this as our 3Vd minus Vc minus V0 minus 3Ve minus Vf minus V0 is equal to 0, which gives us 3Vd minus Ve, and V0 cancels out, so this comes as our Vc minus Vf is equal to 0. This is equation number 7. Now we can easily solve our equation number 7. So from equation 6 we can write to the left side, so this comes as a 3 Vc minus Vf is equal to Vd minus Ve, and equation 7 gives us thrice Vd minus Ve is equal to Vc minus Vf. And this is quite easy. There are only 2 variables and we have 2 simultaneous equations, and their solution, we can say that will be giving us, this will be 9 times Vc minus Vf is equal to Vc minus Vf. or we can say that our, one second, yeah. So this will be 8 we can just take out, so we can say we get this as VC minus VF is equal to 0. Okay, and from here we get that VC is equal to VF. So the 2 points which will be at equipotential, one of there will be other points also, so this will be VC and VF will be at equipotential. So basically equipotential means that we can join them. Similarly, we are going to get that our D and E are also equipotential. Okay, so there is no doubt how to use symmetry, how to use the folding concept. It's a lengthy process, but ultimately you are going to get the correct answer. So we found out we have equipotential, and these two equipotential is our VC is equal to our VF and our VD is equal to our VE. Okay, now we can just you can say connect them. Okay. So let me redraw it here. So this was our A and this was our C and we have our D and this was our B and this is connected like this, and this BF is somewhere here and our E is somewhere here. So we can connect this F with C. So basically means we are going to move this F point here, and there was resistance between A and F. So point F and C are going to overlap, and okay, so let me draw this by dotted line. So this was our F and A is the common one, so we can just denote like this. So this resistance was our R and this resistance will be equal to R. Okay. And similarly there was a resistance, now this E and F, so this is my E and D will be overlapping and E and B are connected, so we can just connect this E and B like this. And there was a resistance between F and E. Okay, so we are going to get resistance between F and E will be like this. So this was R, R, R and R, and this is also our R. So now we can clearly see that this is nothing but parallel combination, this is also parallel combination, and this is also a parallel combination. Therefore we get this is our A, B, and from here we get this as our R by 2, this will be also R by 2, and this will also R by 2, and this is our R. And so this will be 3R by 2, so this is our A, B, and this is R, and from here we get a resistance network that is about 3R by 2. This is about 3R by 2 because all these three are in series. Now these two are in parallel. Therefore we can say that our R equivalent, which is our between R, A, B, will be equal to R multiplied by 3R by 2, and this is R plus 3R by 2, which gives us 3R square. This comes as about 3R square by 2, and this will be 5R upon 2. So here this 2 and 2 square goes away. Therefore we get that the equivalent resistance between A and B will be equal to, this comes our 6 by 5, no, sorry, not 6 by 5 but 3 by 5 times r. Next question. So in this question it states that in YBSC the slit separation is 2 millimeter and distance between the screen and slit and screen is d is 10 meter, wavelength lambda 6000 angstrom. If the intensity of the wave through each slit is I naught, find the intensity of the fringe in front of one of the slits. So we are going to find out in front of the one of the slit. So we can just draw the figure. Suppose if we have slit S1, this is S2 and this is a screen, and the point is just in front of this our S1. Okay, so you can just draw it like this. So this is a basic figure. Therefore we can say that, and we are given this distance is our d and this is our small d. Therefore from the figure we can write that our S1p will be equal to d, but our S2p will be equal to our d square plus small d square. Therefore the path difference will be equal to lambda, and that is equal to our S2p minus S1p, but this small d is very much smaller than capital D. Therefore we can write that his path difference is approximately equal to d square upon 2d, and we can easily find out now our this path difference. So this is a 2 into 10 to the power minus 3 whole square and 2 into 10, which gives us 2 into 10 to the power minus 7 meters. Now we come to a phase difference. Phase difference is about 5, and this 5 will be equal to about 2 pi lambda upon multiplied by path difference. Therefore we get this 5 will be equal to 2 pi 6 into 10 to the power minus 7, and this was 2 into 10 to the power minus 7, which comes as our 2 pi by 3. And the resultant intensity, because it is given that there are coherent sources having equal intensities, therefore we can say that resultant intensity this will be giving us our I, which will equal to I1 plus I2 plus twice I1 I2 and cos of our phi, and this I1 and I2 are equal to I naught. Therefore we can say that our I will be equal to this, we can write this as twice I naught 1 plus cos of phi, and phi is our 2 pi by 3, that will be equal to minus 1 by 2. So we can put here minus 1 by 2. So we get that intensity is equal to over I naught. Next question. It states that the radius of the soap bubble changes from 7 cm to 14 cm. The work done in this process in microjoule is 15,000 minus x. find the value of x. And we know that our soap bubble, it has two surfaces. We have soap bubble and has two surfaces. Therefore, we can write the surface energy that is our E will be equal to twice our sigma times 4 pi r square. This comes as our 8 pi sigma r square. Now we have radius at 7 centimeter and 14 centimeter. So for 7 centimeter we are going to find out initial energy, and for 14 we are going to find final energy, and we are going to subtract it. So we can say our initial surface energy let us put that as E1, and that will be equal to over 8 pi sigma r1 square, and we can simply substitute the values. We get this as E1 is equal to 8 into 22 by 7, 0.04 and 0.07 whole square, and this comes as our 4928 microjoules. Then we come to our final energy, final surface energy. Let us suppose that is our E2, and our E2 will be equal to our 8 pi sigma r2 square. So we substitute that, we get this our E2 will be coming equal to as 19712 microjoule, and the work done that is our W will be equal to E2 minus E1, and this comes as 19712 minus 4928. Therefore we get our work done will be equal to 14784 microjoule, but the work done that is given to us is our 15,000 minus x. So from here we can say that value of x will be equal to 15,000 minus 14784, which is equal to 216. This is the value of x. Next question. It states that the fifth harmonic of a closed organ pipe has the same frequency as the first harmonic of the open organ pipe. Find the ratio of their length. So fifth harmonic closed and first harmonic for open. So first harmonic is basically a fundamental frequency, and it is given that they have the same frequency. So let us start with our open pipe. A frequency for our closed pipe as well as open pipe. So we have a closed organ pipe, and for closed organ pipe there is only odd harmonics are allowed. Only odd harmonics are allowed. Therefore we can say frequency of nth harmonic harmonic. So we can see this f of n for our closed will be equal to n times v, and this comes as our 4 length of our closed, and this value of n is equal to 1, 3, 5 and so on. So from here we can write for fifth harmonic, we can say this is equal to frequency of fifth for a closed will be equal to 5v upon 4 times its length. Now we come to our open. Open organ pipe. And so in this open, all harmonics are allowed. For open, all harmonics are allowed. Therefore, we can write that frequency of nth harmonic will be equal to f of n for open is equal to over n times v, 4 times L open, and it is for first harmonic. So you can say for first harmonic f1 naught is equal to v upon 4 times L naught, 2 times L naught, sorry, 2 times L naught, and it is given that their frequencies are equal. So as per our question, we are given that fifth harmonic for closed is equal to first harmonic for open. Therefore we can say that 5v upon 4lc is equal to v upon 2L naught, and therefore you can say the ratio LC upon L naught will be equal to 5.2. Okay. So this is the ratio of their lengths, respective lengths. Next question. It states that for a uniform cylinder of length L, radius R, the moment of inertia is I1. Now for the similar situation but with the length L2 and R2, the moment of inertia is I2. Find I1 and I2. So we are given two figures, and we are having a cylinder, and this is the axis about which is rotating, and in this case length is L and radius is R. And for second case, everything is same except the length and the radius. In the second case, length is of L by 2 and radius is of R by 2. So here we are given the moment of inertia is I1, and here it is given as I2. We are supposed to find out their ratio. So it is quite straightforward. We know that our moment of inertia of a solid cylinder about the central axis. So you can say moment of inertia of solid cylinder, that is our I, is equal to over half mr square. And we can write that the mass, so our mass will be equal to density multiplied by volume, that is pi r square L. Therefore, for let us call this as case 1 and this as our case 2. So you can say for case 1 we can write that I1 is equal to over half m1 r square, and So we can write this as half mass will be the rho pi r square times L, and this is our r square. Therefore we get that I1 will be equal to 1 by 2 rho pi r4 times L. Now our I2 is nothing but a scaled. Radius is r by 2 and length is our L by 2. For case 2, we can write our M2 will be equal to rho pi, and this comes as r by 2 and L by 2, which gives us that mass M2 will be our rho pi, and we have our r square L upon 8. Therefore our I2 will be equal to our 1 half M2 r by 2 whole square. So this comes as 1 half rho pi and r4 L upon 8, and this will be 32. And we can straightforward write it 64 divided by 64, and we find out their ratio. I1 upon I2, so I2 was our rho pi r4 L upon 64, and this was 1 by 2 rho pi r4 and L, and these are going to cancel out. Therefore we get this will be equal to our 1 upon 2 multiplied by 64, which gives us 32. Okay, so this is quite straightforward. Only the question was written a little bit differently, but they are memory based, so there might be some problem here and there with the question statement. Next question: a spring of stiffness K, spring constant 15 Newton per meter is cut in the ratio 3:1. Find the spring constant of the smaller length spring thus formed. Okay. And we know that as the spring is cut, the spring constant of each spring is going to change. Okay. But we know the relationship between the spring constant and the length. So we know that our spring constant is inversely proportional to length of the spring. Length of spring, or we can say our K is inversely proportional to length L. So this is a relation between the two. Or we can also write this as our K times L will be always equal to constant, which basically means that K1 L1 will be equal to over K2 L2 and will be equal to K3 L3, and this will be continuous process. And so for this, because it is cut in two portions, so we can say that our K1 is the spring constant for our original spring. This is our K1, and our L1, these are the original spring, constant and length, and our K2 L2, these are the new spring constant and length. New spring constant and length. So the length is cut in the ratio 3:1. Okay, so you can say that our can say spring is cut in the ratio 3:1. Therefore, we can say that the larger piece, or we can say the larger length, will be equal to 3/4 times L, and the shorter length will be equal to 1/4 times L, where this L is original length. Therefore, we can write for our original spring, we can write that is our K times L, and K is given to us 15 times L, and we are interested in our smaller one. We can say the shorter length, the shorter spring, we can say this is our K small, length is our L/4, and which will be equal to 15 times L, and this length and length cancels out. Therefore, we get the spring constant for the small will be equal to 60 Newton per meter. Next question. It states that a microscope has an objective focal length 2 cm, eyepiece focal length 5 cm, and tube length 10 cm. In case of normal adjustment, the magnification of the microscope is. So we can solve it directly by the formula, and we know that using the tube length formula, we know that the magnification which is our M will be equal to L upon the focal length of our objective, D upon focal length upon eyepiece, and D is the our nearest point, which is our 25. We simply substitute it. We get this is 10 upon 2 and 25 upon 5, which gives us that magnification is equal to 25. And we can use the standard formula also, and not standard formula but a lengthy process to find out the focal length of the magnification of first our objective, then the magnification of eyepiece, then we multiply them. So answer will be same. Next question. It states that in a region, if the potential depends upon the radial distance from origin as V is equal to AR cube B, then the charge enclosed in the sphere of radius R is equal to. So the basic equation of our potential that is dependent for radius for a sphere is given to us. That's about V is equal to over A R cube plus B, and we can find out the electric field. We can say that our electric field which is our ER is equal to minus dV upon dr, which gives us our minus 3AR square. And then we can use our Gauss law. Gauss law states that for an enclosed surface, we can write this as our E dot dA will be equal to our charge enclosed upon epsilon naught, and our E dot dA will be equal to electric field, we already know, is minus 3 a r square, and dA will be equal to 4 pi r square, which comes as our minus 12 pi a r 4. Therefore, we can say that our charge enclosed will be equal to our epsilon naught and E dot dA, which we just calculated. Therefore, we can say that our charge enclosed will be equal to minus 12 pi a epsilon naught and r4. This is the value of our charge enclosed. Next question. It states that for a given AC circuit, find the power factor. So AC circuit is given to us. So we have a capacitor, resistance, and a inductor. It is connected to a AC source. So this is our 150 ohm, 60 ohm, and 70 ohm. Supply is 220 and 50 hertz. These are the things which are given to us, and we are going to find out the power factor. And power factor is our cos of phi r upon z. So we know that our power factor is cos of phi r upon z, and we can easily find out our z. Z is equal to our r square plus x square. Okay, and our x is our the difference between the two reactances, which is directly given to us. XL and XC are given. Okay, this is our 70 minus 150, which will be coming as minus of 80 ohm. Therefore, we get our Z is equal to 60 square plus 80 square and square root. So Z comes as to us as our 100 ohm. Therefore, the power factor cos of phi is our r upon z is our 60 upon 100, giving us 0.6. And the nature of power factor we can also write from here. So you can say our nature of the circuit or nature of power factor, value of x is our negative, therefore it is basically a capacitive. Which means that current leads voltage. Current leads voltage. We can also find out our phase in case we require, that is our phi. So you can say our phi will be equal to our cos inverse of 0.6. Okay, so this will be our phase angle. And which is approximately 53. So current leads voltage by 53. Next question. It states that A meter bridge shows a null point initially at P. When the unknown resistance R is connected in parallel with 3 ohm, the null point shifts by 22.5 centimeter. Find the unknown resistance. Basic figure is given to us. So this is about 2 ohm and connected in series is about 3 ohm, and this is our wire, and we are connected a supply here, and the null point is suppose somewhere here, point P, and so the bridge, this is basically Wheatstone bridge type of, so the bridge will be balanced, and you can write that for balance condition you can say our left gap resistance upon right gap resistance is equal to left wire length divided by right wire length. And the resistance is given as our 2 and 3. Therefore, left wire, let us suppose, is our L1. So, right wire will be equal to 100 minus L1. So, we can write this will be equal to our 2 by 3 is equal to our L1, 100 minus L1. So, from here we get our L1 is equal to 40 centimeter. Okay. So, initially the null point, that is P, is at 40 centimeter. Okay. Now, we are given that we added a resistance which is parallel with 3 ohm. So, we are given that adding R in parallel to 3 ohm. Therefore, we can write its R equivalent will be equal to 3R and 3 plus R, and it says that our null point shifts. Okay. Therefore, you can say that null point shifts by 22.5. So, initial null point was 40, mu will be plus 22.5, which gives us 62.5. Therefore, we get this our 2 upon same formula, but now the resistance is our 3R upon 3 plus R is equal to, this comes mu is over 62.5, and it will be coming as 37.5, which is nothing but 5 upon 3. And from here we get that value of R will be equal to 2. Okay. Next question. It states that a voltmeter of 400 ohm resistance is in parallel with 100 ohm resistor. This combination is connected with 100 ohm resistor and a battery of 9 volt in series as shown. Find the reading of the voltmeter. So, basic figure is given to us. So, this is 100. It is connected in parallel with the voltmeter, and this voltmeter is having a resistance of 400 ohm. There is a series resistance which is of 100 ohm, and this entire is connected with the battery source. Battery is our 9 volt. And so, let's find out what will be total resistance of the network, and based on this we are going to find out the current, then we can find out the voltage. So in order to find out the equivalent resistance, we just ignore our voltmeter. So this will be equal to our 100 in parallel with 400, and then it comes in series with our 100. Therefore we can say that our R equivalent will be equal to this 100 into 400 divided by 100 plus 400. This will be the parallel combination and plus the series combination, and so we get the R equivalent will be equal to our 180 ohm. So it means now our circuit will be like this. So this will be our R equivalent, and we have a battery of 9 volt. Therefore we can find out the current. So you can see our current I will be equal to our V is our 9 and this is 180, giving us 0.05 ampere, and the voltmeter is in parallel. One second. Okay, so this is our current I, and this is our voltmeter. And ideally the voltmeter is having such a high resistance that this current I approximately flows through our this 100 ohm resistance. So the voltmeter reading, that is equal to V, will be equal to I multiplied by this 100. 1 second. No, this voltage is not high, so let me redefine it. Therefore we can say that so here we are giving current I, and we are going to find out what will be the parallel value of this resistance. So we get this as our RP, and this is current I, and here we are going to have a voltmeter, because the value is the resistance value is mild, not very high, it is only 400. So RP is our 80. So you can say that voltage across voltmeter reading will be equal to current I multiplied by our parallel resistance, which comes as our I is our 0.5 multiplied by 80, which comes as our 4 volt. So this will be the reading of the voltmeter. Otherwise, in case of our ideal voltmeter, the resistance is close to infinity. So all the current should be flowing through this resistance. Okay, no current flow here. But here it is a mild one. So this is over 400 and this is over 100. That's why we calculated it. Otherwise, there is no need to calculate it. Next question. Okay, we have done this. It states that a brass rod is fixed rigidly across supports and welded without any tension in the rod at 27 degrees centigrade. Now it is cooled to minus 43 degrees centigrade. The tension becomes T naught. The temperature at which the tension becomes 1.4 T naught is equal to, I think this is minus X. Find the value of X. We will see to that. And so we are given that there is no tension at 27 degrees centigrade, and the tension is our T naught as minus 43, and it becomes 1.4 T naught at some temperature, that is our x. Okay. So we can use the formula for our, you can say, thermal stress. So you can say for a rod fixed at both ends, the thermal stress is our E alpha multiplied by delta T, and our tension T is equal to our this thermal stress multiplied by our area. So this comes as our E alpha A delta T, and all these parameters are constant except this delta T. Therefore we can say our tension T is proportional to the change in temperature. Now let us use the temperature which is given to us. So we are given that at 27 degrees centigrade our tension T is equal to 0, and at minus 43 degrees centigrade, let us find out what will be our temperature change. That will be equal to 27 minus of minus 43, which is our 70 degree centigrade. Therefore at this temperature the tension is given as T naught, that will be equal to our K times 70. K is our proportionality constant, so K will be equal to T naught upon 70, and it says that at minus x degree centigrade the tension comes equal to 1.4 times T naught. So now for this particular change we are going to find out our change in temperature, that will be 27 minus of minus x, which comes as our x plus 27. Okay. And at this particular temperature the tension is 1.4 times T naught. Let me write it separately with a constant. Therefore we can say that 1.4 times T naught will be equal to what K and x plus 27. K we already know. So K is our T naught upon 70, and this is x plus 27. This is T naught, and T naught cancels out. Therefore from here we get that value of x is equal to 71. Next question. It states that 3 uniformly concentric charged shells are kept as shown. Find the potential of each shell. And the basic figure is given to us. So we have 3 concentric. This is the first one, second one, third one, and the radii for the smallest one it is our A, then it is our B, and the largest one is our C. And the charges they are given for A is our Q1, Q2 and Q3. So our this for spherical shell, let's find out what will be the potential at any point inside the shell and outside the shell. So you can say that, let me rephrase it. So you can say that for a spherical shell of radius r, for a spherical shell of radius r and charge q, we can write that potential at any point inside the shell, potential at any point inside the shell, and let us call this as our V, and so our V will be equal to K upon Q upon R. Any point in that shell, we can denote that point as R, which is less than the radius. And basically it means that the point inside the shell doesn't matter. Wherever the point is inside the shell, the potential will be always equal to constant. Then we can say potential at any point outside the shell, and this case is our R is greater than or equal to capital R, and we are going to have V is equal to KQ upon R. So it means this, where the point is located is important when the point is outside the shell, but when the point is inside the shell, the location of the point does not matter. Okay, so we are given that we have in 3 shells, their radius are A, B and C, and the charges are given as our Q1, Q2 and Q3. Okay, so these are our 3 shells. So let's find out first of all for innermost shell. We can say for shell at R is equal to over A. So first of all, there will be a contribution because of the inner shell, then there will be contribution because of the middle shell, and then there will be contribution because of the outer shell. And so we can say for the shell at R is equal to A, we are having our inner shell is going to give us our K Q1 upon A. Then we are having a middle shell. Middle shell will be K Q2 upon B. And then we are having our outer shell. Outer shell will be equal to our K Q3 upon C. Therefore, we can say that our total potential VA will be equal to K Q1A plus K Q2B plus K Q3 upon C. Then we come to a middle part. Middle shell, which is equal to R is equal to over B. Now, in this case, for the middle one, we have to remember this particular formula. This one. Because for middle one, the value of this R will be equal to B. Okay? So it means the potential because of this charge Q1 at a point which is at a distance B will be equal to K Q1 upon B. Okay? This is the important part here. Therefore, we can say from inner shell from inner shell, this will be equal to k q1 and r, that is distance between is our b, because here in this case our r is equal to our b. Now then come over from middle shell, which will equal to k q2 upon b, and then we come over from outer shell. From outer shell is over k, this is over q2 upon, not q2 but q3 upon c. Therefore we get that our vb will be equal to, this comes as our k q1 plus q2 upon b plus k q3 upon c. Okay. Similarly, we come to our outer part, outer shell, and in this case we have to remember that our for outer we have a r is equal to over c. So once again, from the inner one, inner we are going to k q1, but value of r is over c. For middle, once again it will be k q2 upon c, and for outer we are going to have k q3 upon c. So we get our vc will be equal to k q1 k q2 plus k q3 upon c. Note. Okay, so this is a little bit tricky but quite simple based on the form. Next question. It says that find the net dipole moment of the configuration as shown. So basic figure is given to us. So we have at this point is our minus a0, and here we have in minus 4q, and this point is our 0 comma minus a, and this is our 2q, and here also we have our a comma 0, and this is our 2q. Okay, here the direct dipoles are not given, but we are given the dipoles which are indirect. Okay. But we can use the basic concept of our whether the dipole moment formula can be applied or not, and that we can call as a applicability of dipole moment formula. Okay. We can check that our applicability of dipole moment formula. And that applicability is that the summation of the charge should be equal to 0. Okay, because we know the dipole is like minus q plus q minus 2q plus 2q. So if we enclose that within the surface, the summation will be equal to 0. Therefore, in this case we have minus 4q plus 2q plus 2q is equal to 0. So we can use the summation is equal to 0. Okay. Our net charge is equal to 0. So this is our condition. So therefore, we can use that the dipole moment of the system let us suppose it is our P, then we can write that our P will be equal to summation of our Qi Ri. This is our summation, okay, and it is basically independent of the origin. So first of all, there is no need to, otherwise we can just write this -4 as -2q and -2q. Okay, so we are going to get two dipoles here as well as here, but that is not required. So we are going to check the applicability of the dipole moment. If the summation of the charges is equal to 0, then we can use the dipole moment formula. Okay, because we know for dipole, like there is a -q and correspondingly there will be +q, and that goes on. Okay, and we have to remember this is independent of the origin. Okay. Now let us find out our position vectors. We can say that our R1 is our -a, 0, our R2 is our a, 0, and our R3 is our 0, -a. So let us calculate dipole moment because of each charge. Dipole moment of each charge. So let us find out, that is -q charge, which is at our -a, 0. So we get this our P1 will be equal to -4q multiplied by -a, 0, which comes as 4qa, 0. Next is our charge, which is our +2q, and that is our a, 0, which gives us a P2 will be equal to our 2q a, 0, giving us 2q a, 0. Finally, we are having, okay, both are +2, so this is our +2q, and this is at 0, -a. So we get our P3 will be equal to our +2q 0, -a, giving us 0, -2qa. So we found out the respective dipole moments, okay, and we are going to do their vector addition. So you can say that net dipole moment which is our P will be equal to P1 plus P2 and plus P3, their vector addition. So we simply put their QA0 plus 2KA, 0 plus 0, -2QA. Therefore, we get that our net will be equal to, this comes as 6QA and -2QA, or we can write this as our 6QA I unit vector minus 2QA j unit vector. So this is our net dipole moment, and we can find out the magnitude also. So magnitude will be equal to our, this will be 36 q square a square plus 4q square a square, and that will be 40. So this will be coming as 210 q times a. We can also find out their angle, direction rather. We can say the direction of dipole moment tangent of theta will be equal to for y, and this is our x, and this theta is with respect to positive x-axis. Theta is with respect to positive x-axis. So we get this tangent of theta will be equal to minus 2qa divided by plus 6qa, which gives us minus 1 by 3. Okay. So from here we get theta is equal to minus 18.43 approximately. Okay. So it will be, this is my positive x-axis, so it will be, you can say, points in the here minus, so let's say 18.43. And next question, it states that find the work done to exchange the configuration of three masses from initial state to final state. Okay. And basic figure is given to us. So we are having two triangles, and each is corner is having 200 kg mass. Okay. So the initial state, the distance between the sides is about 20 meters, and it's equilateral triangle. And then for the final, they have increased their size. Masses are also changed. One second, the masses are, this is 200 and this is 300 and 400. Okay. And masses will be same, 200, 300 and 400, but now the distance has been increased to 25. Okay, throughout. So this is our in case 1, and this is our case 2. Therefore we know that the work done will be equal to the difference in their energy. Okay. You can say that work done, that's our W, is equal to our minus delta of U, which gives us our U initial minus U final, and our U will be equal to minus of G summation our Mi Mj upon the distance between the two. So we can find out our case 1. Distance between them is 20, so this is our minus G, and we have this as our 200 times 300 plus 200 times 400 plus 300 times 400. Distance between them is 20, and this initial energy comes as minus G times 10400. Sorry, this is final. This comes as our 13. Similarly, we can write for our case 2. Case 2, we have our final is equal to minus G. Only thing that is going to change is our denominator. So we get this as 200, 300 plus 200, 400 plus 300, 400 divided by 25, 25 and 25. So we get our final is equal to minus of G times 10400. Now we can find out their work done. Work done will be equal to our this will be coming as minus of g, we can take as common, so this will be equal to our 13,000 minus 10400, and this gives us the work done will be equal to about 2600 multiplied by g, and g can be substituted. This is minus 2600, and we have this is 6.67 into 10 to the power minus 11. So this gives us that the work done is equal to minus 1.734 into 10 to the power minus 7 joules. Okay. Next question. It states that a magnetic dipole is placed in uniform magnetic field 800 Gauss at an angle of 30. It experiences a torque of 16 into 10 to the minus 3 Newton meter. Find the work done in slowly moving the dipole from stable equilibrium to unstable equilibrium. And so we know our torque equation. We know that our torque on a magnetic dipole in a uniform magnetic field and that torque is our tau, which is equal to m b sine of theta, and this torque is given to us as 16, so this can be 16 into 10 to the power minus 3 is m is our magnetic moment, and this is 0.08 times 0.5, because theta is given as 30, so sine 30 is our 1/2, and magnetic field is given to us in a Gauss, so that will be equal to our 800 multiplied by 10 to the power minus 4. So we get our B is equal to 0.08 Tesla. And now we come to our equilibrium positions. So for stable equilibrium, the dipole must be aligned with the magnetic field. For stable equilibrium, our dipole is aligned with the magnetic field, which means our theta is equal to 0. And here, under this condition, the potential energy, let us call this as US. US means stable, will equal to minus mv cos of 0, which gives us minus m times b. And for unstable equilibrium, the magnetic dipole is opposite to the magnetic field. For unstable equilibrium, our dipole is opposite to the magnetic field, or we can say our theta is equal to 180 degree. Therefore, the potential energy for our unstable will be equal to minus mb cos of 180, which gives us plus m times b. Now work done is nothing but change in potential energy. Work done is change in potential energy. change in potential energy. So we can simply, our work done W is for our unstable minus stable, which comes as a plus MB minus of minus MB. This is equal to twice MB, and we know both the values. So we can say that our work done is equal to twice magnetic moment is our 0.4, magnetic field in Tesla is 0.08, which gives us 0.064 joules. Okay. Next question states that find the current through 10 ohm resistance as shown in the figure. Okay, so the figure is given to us. So this is 5, 10, 2, 4, and this is 20 volt, and 20, and this is 10 volt. So we are going to use our KVL, Kirchhoff voltage law, and let us suppose current through here is our I1 and current through here is I2, and therefore we can say that the current through here I10, resistance 10, will be equal to I10 is equal to our I1 minus I2. So let us apply KVL in the left part. You can see Kirchhoff voltage law in left loop, and so there is a 20 volt source here. So this we can see our 20 minus I1, and it will be equal to our 5 plus 2 plus 10 I1 minus I2 is equal to 0, which gives us that our 17 I1 minus 10 I2 is equal to 20, equation number 1. And we have KVL now in second loop. KVL in right loop, and from there you can say that our this is 20 here it is equal to, my mistake, 20 equal to, and this comes as our 10 equal to, and we have our I2 times 4 plus 10 I2 minus I1, and this gives us that 10 is equal to minus 10 I1 and plus 14 I2. This is equation number 2. So we have two simultaneous equations and we can easily solve them. From equation 1 and equation 2, we are going to get that our I1 will be equal to 2.754 and our I2 will be equal to 2.68 amperes. Therefore, current through 10 ohm resistance through 10 ohm, which is our I10 is equal to I1 minus I2, so which gives us that I10 is equal to 0.074 amperes. So these were the questions, memory based questions from the morning and evening session that was held on the 24th. So there were, I think, close to 23 or 24 questions. Okay, please remember these were memory based questions, so there might be some, you can see, data here and there, and statement might be misaligned, but the basic idea you get. Okay. So this completes today's part. Thank you.